In this video, we're going to deal with the case of a string being attached and fixed at both ends, and then taking a look at the standing waves that can happen. For a fixed ends, I'm just going to draw a quick little diagram here. So let's imagine we have a string across here, tied across. We'll call that string, and we have the fixed ends. Whoops, sorry about that, right there. So if I get that string vibrating, or I pluck it, if I get it vibrating at just the right frequency, I get that pattern like we saw in the video that looks like that, where basically the string oscillates before that and creates one bump. This is what happens at the fundamental frequency. We call that F1, and we will refer to that as n equals 1. Now, if we change the frequency that it's vibrating a little bit, nothing much happens. We don't create a standing wave. You usually just get a bunch of like little vibrations. But all of a sudden, you hit another frequency, you're going to get this pattern where you get two bumps or two antinodes. There are nodes here, antinode right in the middle, wherever there's a wide bump. Here, node, antinode, node, antinode, node. This is the second harmonic, or first overtone. We call that F2, or n equals 2. And once again, I'm just going to increase it here. If I get and increase it again, these should be equally spaced bumps, by the way. This is a function that my drawing's really bad. But this is the third harmonic, F3, or we can call it n equals 3. You can also call this the second overtone. And once again, notice there's 3 bumps there, 3 antinodes. And you could keep going on, etc., like that. So you may be wondering, okay, is there a way we can predict what frequencies we're going to get these standing waves to happen? Because F1, F2, and F3 are very specific. So how can we go ahead and calculate those? Here's what we're going to do. We're going to apply this. Let's look at string instruments. The fundamental frequency of a string fixed at both ends depends on a couple of things. It depends on the tension of the string and what we call the linear mass density of the string. Now, this will probably come as no surprise to you who have played guitar or anything like that, because when you tune a guitar to play certain frequencies of notes, you basically tighten and I apologize to you musicians out there who are, I don't know the terms, but when you tighten the ends on the guitar, you're changing the tension in the string, and you can tighten, loosen how tightly the strings are held. And you'll also notice that some of the strings you use on guitar are of different thicknesses and different weights. That's what I mean by the fundamental frequency of a string instrument depends on the tension in the string, how much it's stretched, and the mass density of the string. So we're going to use T is the tension of the string in newtons. Mu, we're going to call the mass density, and its unit, U, is basically mass over the total length of the string. And so the unit for that is kilograms per meter. So here's what's kind of interesting about this. It turns out for tension and mass density string, if you get a wave moving down that string, like you pluck that string and it sends vibrations down it, you get a wave. The wave speed on a string is equal to the square root of the tension divided by the mass density. So your textbook has a nice little example in there and says that if you have a 1 meter string with a mass of 50 grams and you put it under tension of 100 newtons, I should say, what is the velocity of waves traveling along the string? If we quickly do this, the unit mass density is m divided by the length of the string. So in this case, 50 grams is 0.0 kilograms over 1 meter. So that's going to be 0.050 kilograms per meter. And V is tension divided by that, and taking the square root. So this is going to be the square root of 100 newtons divided by 0.050 kilograms per meter. And if you calculate that out, you're going to get a wave speed of 4.47 meters per second. If you were to go ahead and pluck that string that was held at 100 newtons, any waves that travel along the string, any vibrations due to you plucking it, are going to be moving at about 4.47 meters per second. We now have a way to set up strings in order to have waves go through. But now we can come to something even more interesting with string instruments. Let's go back to like that earlier diagram we did. Here's my string along here. Now, I'm going to say that this string has a length L in meters. That's how long this string is. Now, it turns out, we're not going to go into the full derivation here. You learn it in upper level physics classes. If you want to know when you get n equals 1, which is the fundamental frequency, and you want to know when n equals 2 or n equals 3, like that, it turns out we now have a way to calculate at what frequencies those are going to happen. And it turns out that formula, Fn, we're going to call it, is Nv divided by 2L, where n is 1, 2, 3, etc. What does this mean? It means at n equals 1, the fundamental frequency is given by V over 2L. Here, F2 is 2V over 2L, or just V over L, and F3 is 3V, and so on. We now have a way of basically calculating at what frequencies we get standing waves in a string, where V will just be T divided by the mass density. By the way, n equals 1, this is the main note played by a certain guitar string. That's the one you usually hear the loudest. Now you do hear the overtones and the harmonics, but for the most part you hear that fundamental frequency. Now, one of the interesting things for you musicians out here there is guitar strings are pretty much, they're slightly different lengths depending on where they're attached on the neck of the guitar, but you really tune those strings by adjusting the tension those strings are under. But for something like a harp or a piano, you use strings of different lengths. You don't have to have them under different types of tension. You can use different lengths. So you can alter the length of a string, or you can alter its mass density, or you can put it under a certain amount of tension. All will allow you to tune the right frequency in to get a standing wave there. Well, I hope you find that a useful review. If you have any questions, please let me know. Other than that, thank you for watching and have a great day.